Have you ever faced a problem, big or small, and immediately started thinking, okay, what's the best way to do this? Could be finding the quickest route or maybe untangling some complicated project. We do this all the time, often without even really thinking about it. But for artificial intelligence, finding that optimal path, well, that's the core idea of search. So today we're taking a deep dive into AI search algorithms. We really want to unpack the core concepts, see how different strategies connect, maybe uncover some surprising patterns in how AI agents think to solve problems, and hopefully challenge your understanding of what intelligent navigation is all about.
And we'll be drawing from our key source, Solving Problems by Searching, and some related notes. These really lay the groundwork for how AI agents plan and act, from the theory right through to some pretty amazing real-world uses.
Okay, let's kick things off right there. When we talk about an AI problem-solving agent, what exactly is that? And why is search just so fundamental?
Well, at its heart, it's an agent trying to reach a goal. The search part comes in because usually the path isn't obvious. It's typically a three-step thing. First, problem formulation, defining the challenge.
Okay.
Second, search, exploring the possible ways to solve it. And the third, execution, actually doing the plan. And that problem formulation step is absolutely critical. It's about creating an abstract model of the world.
Abstract model.
Yeah, think about that Romania vacation example. An agent needs to get from Arad to Bucharest instead of worrying about every single pothole or traffic light.
Right, all the messy details.
Exactly. It simplifies its world down to just cities and the roads connecting them, maybe the distances. This abstraction filters out tons of overwhelming detail. It lets the agent focus. Now, for an agent to just follow a fixed sequence of steps, what we call an open loop system, we usually assume things are, pretty straightforward.
Like what?
Like the environment is fully observable, the agent sees everything it needs to, deterministic actions have predictable outcomes, and known it has the info already.
But the real world isn't always like that.
Not at all. So, if there's a chance things might change, like a road closure, you need a closed-loop approach.
Yeah.
The agent monitors things, adapts, like a self-driving car seeing a drum in-shine sign, a road closed sign, and rerouting.
It's funny, that idea of abstraction, it seems subtle at first, but listening to you, it's clearly essential. Otherwise, the AI would just get completely swamped, right?
Totally swamped.
It's kind of like how we abstract things. Like, I just think make coffee, not move hand this way, grasp handle.
Exactly. And once we have that abstraction, we formalize the problem.
Okay.
There are 5 key parts.
Okay, break it down for us.
First, states.
Yeah.
All the possible situations or configurations. The whole set is the state space.
Got it.
Second, the initial state, where the agent starts. Arad, in our example.
Right.
Third, goal states. What counts as success? Reaching Bucharest, maybe? Or for a vacuum cleaner bot, maybe having no dirt left.
Makes sense.
Fourth, actions. What the agent can actually do, like go to Sibiu.
The moves it can make.
Yep. Fifth, the transition model. This tells you the result of an action. If you're in Arad and take action, go to Zerend, the result is the state Zerend.
Okay, cause and effect.
And finally, the action cost function. This assigns a number, a cost to each action. Could be miles, time, money, whatever. We usually assume costs add up and are positive.
And the aim is the optimal solution, the cheapest path.
Precisely. Lowest total cost path from start to goal.
So if you visualize it, the state space is kind of like a map, a graph. States are points, actions are the roads between them.
That's a great way to think about it. The AI is basically navigating this abstract graph.
So we have this formal setup, but where do these search algorithms actually get used? Let's look at some examples, maybe starting with those standardized problems researchers use.
Right. Standardized problems are super useful. They give everyone a common playground to test and compare algorithms, like grid world problems.
The vacuum cleaner one.
Yeah, the vacuum world is a classic. Simple 2-cell room, maybe, whereas the robot is cell A dirty, is cell B dirty. That gives you 8 possible states right there.
Okay.
Or sliding tile puzzles. The 8 puzzle, 3x3 grid, or the bigger 15 puzzle. We've probably all played with those. Actions are just slide in the blank space.
I remember those. They could be tricky.
They can. And here's a really surprising pattern. Turns out only half of the possible starting positions for, say, the 8 puzzle can actually reach a specific goal state. It's called the parity property.
Whoa, really? So some are just impossible from the start.
Exactly. No matter how clever your search, if you start in the wrong half, you can't solve it.
Huh, weird.
And then there are mathematical problems like Donald Knuth's 4 to 5 problem. You start with the number 4 and use operations like square root, floor, factorial to try and reach any other positive integer like 5.
Factorial. That gets big fast.
Insanely fast.
Yeah.
4 factorial, factorial, factorial. It's like 620 quadrillion factorial. So you get these infinite state spaces and potentially huge numbers. The challenge is finding a path, often a short one.
Okay, so these aren't just games. They push the boundaries of search methods. Now, how does this connect to, the real world?
Ugh. Real-world problems. They tend to be much more messy, idiosyncratic. Route finding is the obvious one. Your phone's GPS, sure, but also routing internet traffic, military logistics, airline travel.
Airline travel seems way more complex than just distance.
Oh, massively. The state isn't just location. It includes time, fare rules, maybe your frequent flyer status, previous flight segments. The cost isn't just money, it's waiting time, seat comfort, points earned. It gets complicated fast.
Right.
Then touring problems, like the famous traveling salesperson problem, TSP. Visiting every city once, lowest cost. Sounds simple, but it's incredibly hard.
But solving it has real impact.
Huge impact. That example of routing school buses in Boston. Using search and optimization saved them reportedly $5 million a year.
Wow.
And you see these techniques in super complex areas too, like VLSI layout, placing millions of components on a chip, or even protein design, trying to find specific 3D structures for molecules.
Okay, so this stuff is powerful, but with all these different problems and approaches, how do we even judge how well a search strategy is doing? How do we compare them?
Good question. First, we need the idea of a search algorithm. It's the engine that explores the possibilities. It does this by sort of overlaying a search tree onto that state space graph we talked about.
Like a tree.
Yeah, the root is the initial state. Taking actions creates branches leading to new states or nodes. The algorithm keeps track of the frontier, the nodes it knows about, but hasn't explored yet.
Okay, so different algorithms explore this tree differently, and some are kind of blind. They don't get any hints.
Exactly. Those are uninformed search strategies. They explore systematically, but without any domain-specific knowledge about where the goal might be.
How do we measure how good they are?
We look at four main things. Is it complete? Does it always find a solution if one exists? Is it cost optimal? Does it find the lowest cost solution? And then time and space complexity. How long does it take and how much memory does it need? Usually measured in terms of B, the branching factor, and D, the depth of the solution.
Okay, so what are some of these uninformed methods?
Well, there's breadth-first search, BFS. It explores level by level, finding the shallowest solution first. It's complete, and it's optimal if all actions cost the same, like 1.
Oh, sounds good. What's the catch?
Memory. Its space complexity is OBD exponential. It has to store the entire frontier, which can grow huge really fast. It's often the memory, not the time, that kills BFS on big problems.
Right, that exponential growth is scary.
Then there's Uniform Cost Search, UCS. It's like BFS, but it always expands the node with the lowest total path cost so far, which we call GN.
So it handles different action costs.
Exactly. It's complete and optimal as long as costs aren't negative.
Mm.
If we go back to Romania, UCS would prioritize a shorter 80-mile road over a longer 99-mile road, even if the longer road looked closer to Bucharest on a map. It cares about the actual cost paid.
Okay, makes sense. What else?
Depth-first search, DFS. This one dives deep. It always expands the deepest node in the frontier first.
Ah, so the opposite of BFS.
Pretty much. Its big advantage is memory.
Right.
Space complexity is only linear, OBM, where M is the max depth.
Yeah.
Much, much better for memory.
But there's always a but.
But it's not complete or optimal. It can easily get stuck going down a really long, maybe infinite path, or get caught in loops if you're not careful.
So memory efficient, but risky.
Right. Which leads to a really clever solution. Iterative Deepening Search, IDS.
Iterative deepening. How does that work?
It's a hybrid. It basically does a DFS, but only down to a certain depth limit. First depth 1, then depth 2, then depth 3, and so on. It repeats the search, going deeper each time.
Doesn't that waste time redoing the early parts?
A little bit, yes. But the number of nodes at deeper levels usually vastly outweighs the shallower ones, so the overhead isn't as bad as you might think. And the payoff is huge.
Which is?
You get the completeness and optimality for unit costs of BFS, but with the fantastic memory efficiency, that OBD space of DFS. It's often the go-to uninformed method when your state space is just too big for BFS's memory appetite.
Wow, that's actually pretty ingenious, combining the best of both. It really highlights that trade-off, doesn't it? Memory versus time, or maybe recomputation for memory savings?
Absolutely. And speaking of saving time, there's another trick. Bidirectional search.
Searching from both ends.
Exactly. You search forward from the start and backward from the goal, hoping the two search frontiers meet in the middle.
Does that actually speed things up?
Theoretically, hugely. Instead of exploring one tree of depth D, you're exploring two trees of depth roughly D2. Since the complexity is often exponential, like b to the power of d, changing that b to d2 can mean exploring way fewer nodes. Think bd2 plus bd2 instead of bd.
That sounds amazing. Why isn't it always used?
Well, you need to be able to efficiently compute predecessors to reason backward from the goal. And managing two frontiers adds complexity. But when it works, it's powerful.
Okay, so that's uninformed search. Systematic, but maybe inefficient. What if the AI could get some hints, some sense of direction?
Ah, now you're talking about informed search or heuristic search. This is where we give the agent some extra knowledge.
Through a heuristic function, usually written as HAN. This function estimates the cost from the current node n all the way to the goal. It's like a knowledgeable guess, domain-specific guidance.
So it's like a shortcut estimate.
Sort of. A common first approach is greedy best first search. It simply looks at the heuristic value, HAN, for all nodes on the frontier and picks the one with the lowest estimated cost to the goal.
So it just goes for whatever looks closest.
Yep. Let's use that Romania example again. If our heuristic is straight line distance to Bucharest, Arad to Sibiu looks pretty good. Greedy search might jump there quickly.
Sounds fast.
It often is, but it's greedy. It only looks at the estimated future cost, ignoring the cost already spent to get there. So it can easily lead you down a path that looks promising initially but ends up being much longer overall, like taking that path through Sibiu and Figueres, which seems direct but is actually 32 miles longer than going via Râmnicu-Vâlcea.
So it's fast but not necessarily optimal.
Exactly. It sacrifices optimality for speed.
So how do we get both speed and optimality? That's the holy grail, and it leads us to probably the most famous informed search algorithm, A-search, pronounced A-star.
Hey, okay, what's its magic?
It combines the best of both worlds. Its evaluation function, FEN, considers both the cost already incurred to reach node n, which is GN, and the estimated cost from n to the goal, HAN, so FN plus HNN.
So it balances past cost with estimated future cost.
Precisely. And for A to guarantee finding the optimal solution, the heuristic HN needs a crucial property. It must be admissible.
Admissible, meaning?
Meaning HN must never overestimate the actual cost to reach the goal. It has to be optimistic or, at worst, perfectly accurate. Can underestimate, that's fine, but it can't promise a shorter path than is actually possible.
Like an honest GPS that gives the true minimum time?
Exactly. There's also a related, stronger property called consistency, or monotonicity. Basically, it means the heuristic values along any path shouldn't decrease by more than the actual step cost. If a heuristic is consistent, it's also admissible.
And why is this admissibility so important for A?
Because if HAN is admissible, and consistent heuristics are even better, A is guaranteed to find the lowest cost path. And not only that, it's optimally efficient in a sense. No other optimal algorithm that uses the same heuristic is guaranteed to explore fewer nodes than A. It focuses on the nodes that are genuinely promising.
Okay, A sounds amazing. Optimal. Efficient.
Well,
What's the catch this time?
memory, again. Just like BFS, A generally needs to keep track of all the nodes it has reached and the entire frontier. For really large problems, even with a good heuristic guiding it, the number of nodes can still grow exponentially and just fill up all available memory.
Our memory again? It seems like the eternal problem in search. So how do we deal with A's memory hunger?
That's where memory-bounded algorithms come in. They try to get the benefits of A, but within limited memory. One key example is Iterative Deepening IDA.
Like IDS, but for A.
Exactly. Instead of iterating on depth, IDA iterates on the F-cost GHA day.
Yeah.
It does a depth-first search, but prunes any path where the F-cost exceeds a certain cutoff. Then it increases the cutoff and searches again.
So it avoids storing the whole frontier.
Yes. It gets the optimality of A with an admissible heuristic, but uses only linear space, like DFS. The downside is it re-explores nodes. But for huge problems where memory is the absolute limit, like solving large sliding tile puzzles, IDA is often the only viable option.
That's clever. Any other memory-saving tricks?
There's simplified memory-bounded A, SMA. It works more like a regular A, but has a fixed memory limit. When it runs out of space, it finds the node on the frontier with the worst F value, the least promising one, and drops it.
Just forgets it.
Not quite. It backs up the forgotten node's F value to its parent. This way, the parent remembers the quality of the best path in the subtree it just pruned. So if all other paths start looking worse later, SMA might decide to re-explore that forgotten path. It's clever, tries to find the optimal solution if possible within the memory limit, but can sometimes get stuck thrashing, repeatedly dropping and regenerating nodes on really hard problems.
Okay, so ways to manage memory. What if you don't strictly need the absolute optimal solution?
Then you might use something like a weighted A search. Here, you tweak the evaluation function fn plus whn, where ABUH is a weight greater than 1.
So you give the heuristic more importance.
Exactly. This makes the search more greedy, pulling it towards the goal faster. It explores fewer nodes, so it's quicker, but you sacrifice the guarantee of optimality. You might find a solution that's, say, within 10% of optimal, but much faster. It's a satisficing approach, finding a good enough solution quickly.
That makes sense. Sometimes good enough and fast is better than perfect and slow, or perfect and impossible due to memory. It really shows that tension between perfection and practicality. Okay, this is maybe the most fascinating part for me. We've talked about these heuristics, AAN, these magic estimates, but where do they actually come from? How does someone invent a good heuristic?
That is a fantastic question, and it's really where a lot of the art and science of AI problem solving lies. One of the most powerful techniques is problem relaxation.
Relaxing the problem, like making it easier.
Exactly. You take the original problem's rules and you remove some constraints, make it simpler. The key insight is this. The cost of the optimal solution to this easier, relaxed problem can serve as an admissible heuristic for the original, harder problem.
Whoa, okay. How does that work? Give me an example.
Let's go back to the 8 puzzle. The normal rule is a tile can only move into the adjacent empty square.
Right.
Relaxation 1. What if we relax that to say a tile can move anywhere? Then, to get a misplaced tile to its correct spot takes exactly 1 move. So the number of misplaced tiles becomes a heuristic, let's call it H1. The optimal cost in this super relaxed problem is just counting how many tiles are wrong.
Okay, that's simple. And it underestimates, so it's admissible.
Correct. Relaxation 2. What if we relax it differently? A tile can move 1 square horizontally or vertically, even if another tile is already there. Now, the shortest path for a tile is just the number of horizontal plus vertical steps it needs to take the Manhattan distance. Summing these distances for all tiles gives us heuristic H2.
Ah, Manhattan distance. I've heard of that.
And H2 is generally better than H1. Because moving 1 step, Manhattan, is a tighter relaxation than moving anywhere, H1, H2 gives a higher, more accurate estimate of the remaining cost. It dominates H1, meaning H2n is always greater than or equal to H1m.
And a dominating heuristic means A works faster.
Yes. A with H2 will explore significantly fewer nodes than A with H1 to find the optimal solution. There are even programs like Absolver that can automatically generate heuristics by analyzing problem definitions and finding relaxations.
That's amazing, automating heuristic discovery. What other ways are there?
Another really powerful technique, especially for puzzles like the 15 puzzle or even bigger ones, is pattern databases.
Databases of patterns.
Sort of. You pick a subset of the problem, like maybe just getting tiles 1, 2, 3, and 4 into their correct positions, ignoring all the others. Then you pre-calculate and store the exact optimal solution cost to solve just that subproblem from every possible configuration of those specific tiles.
So you build a giant lookup table for parts of the puzzle.
Essentially, yes. During the main search, whenever you encounter a state, you look up the configuration of your chosen pattern tiles in the database and use that stored optimal cost as your HAN.
Clever. But does it get even better?
It does. With disjoint pattern databases, this is a really cool insight. What if you create multiple pattern databases for sets of tiles that are completely separate disjoint? For example, one database for tiles 1 and 8 and another for tiles 9, 15 in the 15 puzzle.
So they don't overlap.
Right, because moving a tile in the first set never affects moving a tile in the second set, except for using the blank space, which you handle carefully. You can calculate the heuristic for each disjoint set and then simply add them together.
You can just add them.
Yes, and the sum is still an admissible heuristic, but it's much, much more accurate than either pattern database alone or even Manhattan distance. This technique led to massive speedups, like solving 15 puzzles thousands of times faster and making even the 24 puzzles solvable. It's a fantastic example of finding structure in the problem.
That's genuinely surprising. Adding heuristics because the parts are separate. Wow. What about huge problems like map routing?
For things like continental scale rope finding, pre-computing everything is impossible. There, they often use landmark points.
Landmarks, like major cities.
Could be, yeah. You pick a few dozen strategic points across the map, then you pre-compute the optimal path cost between all pairs of landmarks and also between every single node, like a road intersection, and each landmark.
That sounds like a lot of pre-computation, but maybe manageable.
It is. Then, during a query, finding a route from A to B, you can use these pre-computed distances to quickly estimate the remaining distance. A really effective method is the differential heuristic. It uses the triangle inequality with landmarks. For a landmark L, the distance from your current node N to the goal must be at least the difference between the distance from N to L and the distance from the goal to L. You take the maximum difference over all landmarks.
And that works well.
Amazingly well. It's efficient to compute and provides a good, admissible heuristic, allowing online map services to find optimal routes across vast networks in milliseconds.
Okay, that makes sense for maps. Is there a role for machine learning here too? Can AI learn heuristics?
Absolutely. You can learn heuristics from experience. You solve lots of example problems and feed features of the states, like for the 8 puzzle, number of misplaced tiles, Manhattan distance, maybe other things, and the actual remaining cost into a machine learning model.
So the model learns to predict the cost.
Exactly. It might learn a good combination of known features or discover entirely new patterns that correlate with solution cost. These learned heuristics aren't always guaranteed to be admissible, but they can be very effective in practice, especially for complex domains where designing heuristics by hand is really tough.
This is incredible. It's like AI researchers are finding all these clever ways to inject intelligence by simplifying, by pre-calculating, by finding patterns, even by learning from data. It's not just brute force search, it's engineered guidance.
That's a perfect way to put it. And the impact of a good heuristic is dramatic. We measure it using the effective branching factor, B. A perfect heuristic would guide the search directly to the goal, making B close to 1. A poor heuristic means the search explores lots of dead ends, making B much higher, closer to the actual branching factor, B.
So lower B is better.
Much better. It means the heuristic is successfully pruning away large parts of the search tree. And remember that trick with disjoint pattern databases. It highlights another useful pattern. If you have several admissible heuristics for the same problem, H1, H2, H3, you can create a new combined heuristic by just taking the maximum value, H1n, H2n, H3n.
Taking the max.
Yes. The resulting heuristic is still guaranteed to be admissible since none of them overestimate and will dominate all the individual ones. It gives you the best hint available from all your sources at any given state, leading to potentially even better search performance.
Okay, putting this all together, it feels like we've gone from basic problem definition to these really sophisticated ways of guiding the search. The constant push for better heuristics and more memory-efficient algorithms seems crucial for AI's progress.
It really is. It's what allows AI to tackle problems that were completely intractable just a few decades ago, finding optimal solutions in enormous state spaces, whether it's logistics, design, or scientific discovery.
If you connect this to the bigger picture, the evolution of these search techniques, especially the invention of heuristics, it's like we're watching AI learn how to navigate complex information landscapes more and more effectively.
It's a continuous refinement, absolutely, making the impossible possible by finding clever ways to represent and explore possibilities.
So for you listening, what does this all mean? Well, next time you ask your phone for directions or you see an AI generate a complex design, remember what's happening under the hood. There's an agent abstracting the world, defining states and actions, and then using these powerful search algorithms, guided by clever heuristics, maybe learned, maybe pre-computed, maybe derived from relaxation, to find an efficient path through a mind-boggling number of possibilities. We've covered a lot today, from defining the problem to the nitty-gritty of algorithms like BFS, DFSA, IDA, and the incredible ingenuity behind crafting those heuristic functions. It's this world of trade-offs, memory for time, optimality for speed, all driving towards finding that path to the goal.
And that continuous quest for better heuristics, for more scalable algorithms, it keeps pushing the boundaries. It turns intractable problems into tractable ones, opening up new possibilities for what AI can achieve.
Which leaves us with a final thought, something for you to mull over. As AI gets better and better at this kind of guided search, at formulating problems and finding solutions within those formulations, what's the next frontier? Will the truly big breakthroughs come from AI discovering entirely new ways to abstract the world, creating its own models that we haven't even thought of? Or perhaps will it move beyond explicit search altogether, learning to solve problems more intuitively, maybe through deep learning pattern recognition without needing to explore a state space step by step? Something to think about for your next deep dive.